Hello, everybody. This is Sunday. It's March 19th, and we are heading into week 10 of our online astronomy course. And oh my gosh, we are almost through this long winter of snow after snow after snow. But tomorrow, on Monday, March 20th, it is the vernal equinox, the spring equinox, when the sun passes over Earth's equator going from south to north. And that will happen here in Salt Lake, or in Ogden, where I am, but in Salt Lake City is the time I have, will happen at 3:26 p.m. So 3:26 p.m., leave winter of this year behind you, and welcome to spring, when we will have our first snows. So our first snows of spring are coming this week. Well, we just finished up Module 9. Module 9 is on the sun. And so you've learned about our star. But our sun is just one of untold hundreds of billions of stars that are in our galaxy. And so now we turn to a study of stars themselves. And if you look up in the night sky in a dark place, you're overwhelmed by the number of stars that are up there. If you're in the city, actually you can see a good number of stars, even under city lights. If you live up on the East Bench the way I do, it's not bad, but it's not like it is going behind the mountains and up into the mountains and being able to see a sky full of stars. And we've wondered about the stars from time immemorial, before there were written records, and what are these things we're looking at? How large are they? How bright are they? How massive are they? How do they compare with our sun? All these questions have challenged astronomers and philosophers for hundreds and thousands of years, because the stars are so far away that there's no way we could ever have sent a probe out to even the nearest star and take a sample of it and see what it's like. All we can do is look at the light from the stars. And so the question is, what can we learn from starlight and from seeing how stars move? And yes, stars do move. If you look at them closely, they do move. So let's start learning about the stars. And the first thing to do is know that we can, as Earth goes around the sun, stars are very far away, but some stars are a lot closer than the more distant background stars. And so, as Earth goes around the sun, you look at the stars from one side of Earth's orbit and then the other side of Earth's orbit. So you're looking at the stars from two different points of view. And that means we can use an old surveyor's technique, the technique of triangulations, where if you see something from a known distance apart, we can then look at the angles at which we're looking at that, and our lines of sight will meet out there in space where the star is. And by using a little bit of math, we can find the distance to that star, that object, whatever we're looking at. Surveyors might find the distance to a mountain peak. It's very far away. We can survey at least the very nearest stars. But to do that, when we're on opposite sides of Earth's orbit around the sun, so if we're on one side of the sun in our orbit and on the other side of the sun in our orbit, we have to know that distance between those observation points. We have to know the baseline for the measurements. And what has really held us up is that we have not known a reliable distance to the sun. So we didn't know for a long time how big Earth's orbit was. In fact, it wasn't until the 1760s that the problem was solved. And the problem was this: if you're going to make measurements, of the distance to something, then you have to know you're measuring those angles, those angles to triangulate on the sun, say, to find out the sun's distance at the same time. Now, that's not true for going around the sun. We can look at a star from one side of Earth's orbit and the other side of Earth's orbit. But if we're trying to find out the distance of the sun is always shifting its motion in the sky. And so if we're going to make a measurement, we have to know we're looking at the sun at the same time. Now, that was really a challenge. And so what did they do? They relied upon something happening on the sun that they could look at and see exactly where the sun was at that time from any point on Earth. And that event was a transit of Venus. Venus would move in front of the face of the sun. It did so in 1761 and 1767. It does them about twice every century. And in fact, the video I showed you in the last module of the sun, just sitting there over a year, if you look about 12 minutes in, you'll see Venus going across the sun, because that happened during one of the rare transits of Venus that happened in this cycle. So astronomers went on opposite sides, went all over the globe. As a matter of fact, it was an international effort. A lot of these nations were at war with each other, but still they cooperated because the question was so important. And they sent astronomers out all over the world. It was hazardous duty. Several of them were killed, but they managed to measure the exact position of the sun from two different points on Earth. And from that, we could figure out the distance to the sun for the first time. And they got a pretty accurate value. And so they could use that value. If they knew the distance to the sun, they know the distance. If I'm looking from one side of the Earth's orbit to the other side, then they know the distance between my eyes and those two sides of Earth's orbit is the diameter, the distance across Earth's orbit. So they have their baseline. So all they had to do now was to find a star whose parallax shifted slightly. And parallax is the name of what they were looking for. They were looking for an apparent shift in the star's position. And let me show you why that is. Why would a star ever shift position? We're going to do our own experiment here. So I hope you'll cooperate with me. And just sit back in your chair and imagine that your nose is your sun, is the sun. And when one eye is open, you're looking out from one side of Earth's orbit on Earth. So your eye is Earth. And here you're looking out from one side of Earth's orbit around the sun. And if you close that eye, open up the other eye, you're looking out from the other side of Earth's orbit around the sun. Now we're going to let your thumb be a nearby star, relatively nearby star. Not the screen of your device that you're watching this on, computer, iPhone, whatever it is, tablet, just pick a star in this background and look toward it and close one eye, doesn't matter which eye, and then put your thumb over that star. So now you're seeing the star, the nearby star, your thumb, covering up a distant star from one side of Earth's orbit. Now, don't move anything. Don't move your thumb. Don't move your head, but change which eye is open. And the question is, did your thumb appear to shift? And the answer is yes. Now, if it didn't, you're holding your thumb too close to your face. Hold your thumb, oh, I don't know, about at least a foot from your face, at least a foot from the screen. And if you do that, you'll see a real shift of the apparent position of the nearby star against the distant background stars. And that is called the star's parallax. And so you can find out what how much the angular position shifted by. You know, if I'm pointing toward where it appeared to be one time and where it appears to be the other time, there's an angle between those two directions, and that is the angle of parallax. And it's very, 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 very small. I mean, you know, we've talked about how 1 degree is divided up into 60 parts called arc minutes. So excuse me. Yeah, 1 degree is divided into 60 parts called minutes. So there's 60 degrees in a minute. The moon is about 30 arc minutes wide, half a degree wide, 30 out of 60. So the moon is about 30 arc minutes wide. So, you know, an arc minute is 1/60th of a degree, pretty small, but we have to go smaller still to describe the apparent difference in a star's position. To describe its parallax, we have to go smaller. So we divide a degree up into 60 parts. And if you divide a minute into 60 parts, what do you get? A second. So these are arc seconds. 60 arc seconds makes an arc minute, and 60 arc minutes makes a degree. And that means 60 times 60 is 3,600. So an arc second is 1/3,600th of a degree. And it's that tiny of shift that astronomers had to look for, even in the very nearest stars. And it took them forever to do it. But once they knew the distance to the sun, they could get a pretty good value. Now, in about 1839, they finally accomplished it. And I want to show you this book. Here's a book. It's very old. You know, let me open it up here and show you the title page. Here we go. This is you can see right here. Here it is. It's an introduction to astronomy. It is a textbook for the students of Yale College, and this is published, maybe you can see down here at the bottom, in 1839. So this is just a few years, well, about 40 years after a decent size for the distance from the Earth to the sun. The astronomical unit was measured. So here it is. Now, it's an interesting book because this is what astronomy was at the time. So here it is. It's that thick. How much of this book is about the solar system, how much about stars, how much about galaxies? Well, here's the deal. Okay. This much of the book right here, this portion of the book is about the solar system. Describes the comets, the planets, the moon, and so on. Now, only this tiny section that's remaining, that tiny section right here in my hand that you can see, that tiny section is where we first encounter the fixed stars and system of the world, part 3. And then you have to pass through even more material because it talks about the constellations and everything else. It doesn't tell you what stars are because they didn't know. But finally, back here on page 266, almost at the back of the book, they're talking about the immense distance of the stars. And the book says they are still points when viewed with the highest magnifiers. And that is still true today, that they are still points. We cannot resolve a star. They're just too small and far away. However, and this is a footnote in the book, and I'll read it to you, okay? It says that very recent intelligence informs us that Professor Bessel of Königsberg has obtained decisive evidence of an annual parallax in the star 61 Cygni, amounting to 1/3 of an arc second. Remember, we talked about how small arc seconds are. This is about 1/3 of an arc second, 0.3136 arc seconds. This makes the distance of that star equal to 700 times the distance to the sun, a distance with which it would take light 10.3 years to traverse. So that is the first time the distance to a star was measured. Right there, and they inserted it as a footnote. As this book went to press, they just had to tell people that the problem of all the centuries had been solved. Well, amazing. Now we know that there are stars that are closer than 61 Cygni. And today we know that the closest star is called Proxima Centauri. It's located in the constellation of Centaurus. It's actually a binary star with its companion star Alpha Centauri, which is the brighter one. And they are together about 4 light years away from us. That is, it takes light 4 years to get to us from those stars. And so we say they are 4 light years away. So light years is a distance. Now, that's the nearest star. And we're going to be talking about stars on the other side of the galaxy. And so actually, light years is not a convenient measure. So we're going to use another measure. And this one sounds really weird. Really, really weird. And it is called a parsec. P-A-R-S-E-C. It stands for parallax second. And what it is, as you go away from Earth, farther and farther and farther, then the radius of Earth's orbit around the sun gets smaller and smaller and smaller from your point of view. Everything gets smaller as you move away from something. The mountains look smaller when they're far away than when they're close up. So as you move away from Earth, that distance looks smaller and smaller and smaller and takes up a smaller angle of view from your point of view. And when you get so far away that the radius of Earth's orbit has a width of 1 arc second, we say that it is 1 parsec away. And one parsec turns out to be about 3.24 light years away. So even the nearest stars, Proxima Centauri, is a little bit over a parsec away. And so we expect other stars to be many, many parsecs away from us. But the important thing is, with parallax, the distance, the probing, the finding distances in the universe had been solved. And today we have sent up spacecraft. Most recently, we have sent up a spacecraft called Gaia that measured the parallax of over 1 billion stars in our own Milky Way with great, great precision and accuracy. And so we now have can make a model of the stars individually in our Milky Way galaxy and how they move. And we'll talk about how they move a little bit later. But Gaia can make all sorts of measurements of these stars and really catalog their properties. So we live in an amazing time where the amount of data flowing back to Earth from orbiting observatories is overwhelming. It's like trying to drink from a garden hose. Now, what else do we want to know about stars? Okay, we need to know how bright they are. Now, brightness is a funny term and is really not very good, because if I have a flashlight and I shine it right in your eyes, right next to your eye, that could be blinding. But if I walk away from that flashlight until I'm on the other side of the room, it's not that bad. And if I'm, across the street doing it, then it might be annoying, but it's hardly blinding, because brightness declines with distance. And it turns out, if you have a source of light like a light bulb, and I look at the light bulb, and then you move twice as far away, it looks 1/4 as bright. And if you move 3 times farther away, then it looks 1/9 as bright. If you move 4 times as far away, guess what? It's 1/16 as bright, 4 squared. And so it's called an inverse square law. So light follows an inverse square law. And so what we want to know is not how bright the stars appear in the sky. I mean, we can look at them and tell how bright a star is, but looking at that apparently bright star doesn't tell us whether it is really intrinsically putting out a lot of energy, or if it just happens to be very close to us. Sirius, the brightest appearing star in the sky, is the brightest because it is close to us. Yes, it is a bright star, but it appears to outshine all the others because it is sufficiently close to us. So we want to know how stars really, how bright they are intrinsically. We want to know their luminosity. And luminosity just means how much energy per second leaves that star's surface. And we've already seen that the sun has a luminosity of 4 times 10 to the 26 watts. And remember, that is 4 million 100-watt bulbs worth of energy per second, measured in watts. So we want to know the wattage of the stars. The luminosity of the stars is one of the things that we want to know. Now, we now understand what the luminosity of a star depends upon. And remember back in module, I guess it was module 4, that we learned about light and about black body radiation? Well, as I told you back then, stars are black bodies. That is, they heat up, they first emit red light and heat up more and more. They emit more blue and light, more and more blue light. And also they get brighter and brighter and brighter. Remember when I turned up the bulb in that video and it went from a dull red to a glowing light of all colors, and the blue was really bright there in the spectrum that you saw off to the side? If you remember that, turns out that stars are black bodies. Now we know how black bodies give off radiation. You know, the luminosity of a star depends upon two things, and only two things. It depends upon the star's surface temperature. And we measure surface temperature in degrees Kelvin in astronomy. Now, there's nothing mysterious about degrees Kelvin. 0 Kelvin is absolute zero, the coldest you can get. If you want something to compare to, you know that water freezes at 0 degrees Celsius, freezes at 32 Fahrenheit. It freezes at 273 Kelvin. Water boils at what? 100 Celsius, 212 Fahrenheit, and 373 Kelvin. So you'll never have to convert, degrees in centigrade or Celsius to degrees Kelvin or convert to Fahrenheit. Not interested in doing that. Just remember that freezing is 273, boiling is 373, and that's all you need to know those roughly. Because you might remember that the surface of the sun was 5,770 something degrees Kelvin. And the center of the sun was around 15 million degrees Kelvin. So just remember numbers in Kelvin and have a rough idea of what that means. That's all you have to do. Don't worry about it. Well, the luminosity of a star depends upon two things, as I was saying. The temperature in degrees Kelvin, the surface temperature of the star in degrees Kelvin, raised to the 4th power. That is, the surface temperature is multiplied by itself 4 times. 1, 2, 3, 4. For instance, 2, 4, 8, 16, multiplying by 2. 2 by itself 4 times. It also depends upon the star's size, because the temperature tells you how much energy per second each little square meter of the star's surface gives off. Now I have to multiply that times the number of square meters on the surface of the star. And remember, like any sphere, the surface of a sphere is 4 pi r squared. And so the luminosity of the star depends upon the square of its radius and the temperature to the 4th power. And don't worry, you're never going to have to plug numbers into that equation. But you can use that equation to compare our sun's luminosity to another star's luminosity. And there's examples in the introduction to this module showing just how to do it. And it's very easy. You can't quite do it in your head because you have to take the 4th power of something to square something twice. And that might be a little bit challenging. So you might need a calculator for that. But that's not hard, and you will not have to do that on an exam. Okay. Um, Now, there's another thing that since time immemorial we have used to talk about the stars, and that is how bright they appear in the sky. And we can go way, way back to an ancient Greek named Hipparchus, who made a catalog of 850 something stars. And to each one, he assigned a brightness. Now, what do we call somebody who comes in first place in a race? There's first place, second place, third place behind them. But the supreme is first place. And so he assigned a magnitude of 1 to the brightest star in the sky. And he assigned a magnitude of 6 to the dimmest appearing star in the sky, the dimmest you could see with the naked eye. And so the brightest stars that you can see in the sky with your naked eye are first magnitude stars, and sixth magnitude stars are the dimmest stars you can see with the naked eye. Now, if you really go out in the middle of the desert, something like that, you might see even dimmer stars. But under ordinary conditions, away from a city, just looking up at a night sky, but still some lights around, you'll go from 1 to 6, where 1 is the brightest, 6 is the dimmest. And those numbers mark a star's apparent magnitude. Apparent magnitude. And we signify that with a lowercase m. Lowercase m. But again, that doesn't tell us how bright the star is, because this is how bright stars appear in the sky. And if the stars move in and out away from Earth, that their brightnesses would change, their apparent magnitudes would change. So we want some measure of brightness that puts all the stars at a constant distance. Now, we can't get a tow truck to go out there and haul in the stars until they're all at a certain distance, but we can do it mathematically. And when you do that, it turns out that there's a number called a star's absolute magnitude. And that is the apparent magnitude the star would have if it were carried in or out to a distance of 10 parsecs from Earth. So a star's absolute magnitude, that's a capital M to distinguish it from the apparent magnitude, lowercase m. The absolute magnitude is how bright the star would be if it were 10 parsecs away from us. So we have these two types of distance measurement, apparent magnitude and absolute magnitude. And there is a very important equation, because, if you know a star's apparent magnitude, and if you know its absolute magnitude dimmed by distance, then there should be a way of figuring out from those two numbers, the apparent magnitude and the absolute magnitude, how far away the star is and get the star's distance. And there is. It's a very simple equation. You'll find it in the introduction to this module. It's not in your text, but you're still responsible for this, because this is probably the single most important equation that astronomers use. Because if you can measure the distance to the stars in parallax, in arc seconds, then you can find the distance to the star in parsecs. So you go out, you measure the distance of the star you measure that angle in arc seconds, and that means you can that means the star's distance, and it all hangs together very well, because this will give you the distance to a star even if you can't measure its parallax. And in fact, the Hubble Space Telescope was built to measure the absolute and apparent magnitudes of very distant stars and use this formula to get their distances. So it's really amazing. But you might be saying, hey, I thought we had to know the distance in the first place to get the absolute magnitude. Now you're telling me we can use the absolute magnitude and the apparent magnitude to get the distance. This is all circular. It doesn't make any sense. And that argument is absolutely right. And what I haven't told you yet, and we'll talk about next time, is there's a way of getting a star's absolute magnitude without knowing its distance. It has to do with pulsating variable stars. And these stars are the greatest gift to astronomy. And I'll talk about that next week. So we've learned a lot of stuff just from looking at the light of stars and how stars change as we change position, looking at them in our orbit around the sun. What else do we know about the stars? Well, we know, for instance, something about their surface temperature, because we can take the spectra of the stars. Remember, we talked about taking the spectra of stars, looking at a star's light. It goes through a prism that splits the light into the colors, and we can see the dark absorption lines in the star's spectrum. And so in the early 1900s, there were a bunch of women at Harvard Observatory, and they were hired by Pickering, a man named Pickering, an astronomer, and he paid them to look at spectra after spectrum after spectrum of all these stars. You would go out, take pictures of a field of stars through a prism that would break all of the stars spectra up so you could look at them. And so the women would sit and look through their magnifying, and it was up to them to try to find some order to this. Which spectra look alike, which look different. It's somewhat like Darwin's work with seashells, that he classified that here, these look a little bit alike, these look a little bit different. And that's important work, because if you can find similarities and differences in stars, then you can begin to understand them. And so the women who did this, the women like Wilhelmina Fleming and Annie Jump Cannon, who did this work, invented modern astronomy, and they are real heroes for astronomy. And now there are special prizes in their name given by the American Astronomical Society. But they looked at spectra and they arranged them in order, and they didn't know what to call them, so they gave them letters of the alphabet, A, B, C, D, E, F, G. And so they tried to find a way that patterns would all merge into one another and move from one another. So you might say these patterns would move into these patterns, would move into these patterns, and they would arrange those. And they found out that when they did that, the order of the alphabet that they'd started with had been scrambled. And it turns out that their scale was a temperature scale. And the order of the letters today we know are O for the hottest stars. O stars are the hottest stars. B, A, F, G, K, M. O, B, A, F, G, K, M. From hottest O stars to the coolest M stars. Those are the spectral types. And it's one of the most pieces of valuable information we have about the stars. And that was invented by these amazing women at Harvard Observatory. So OBAFGKM, and you really should know that. And here's a little mnemonic, a little memory device that you know, generations of astronomers, have memorized to memorize that spectral sequence. And here it is from O stars, O, B, A, F, G, K, M, down to the M stars. And the saying is, O, be a fine girl or guy, kiss me. O, B, A, F, G, K, M. And so if you just remember that O, B, A, F, G, K, M, you know the spectral sequence from hot to cold, from O stars to M stars. Now, in fact, each spectral type is divided into 10 classes. So there are O0 stars, there's O1 stars, there's O2 stars, all the way up to O9. And then you get the B stars, B0 through 9, and then A0 through 9, and so on. And the further you go down, you go from hot to cool. Our sun is a G2 star. And so our sun has a spectral type of G2. Pretty cool. So that is extremely valuable information that you can get about stars. Now, once you have, this information about the stars, what can you do? What can you do with it? And what you can do with it is to arrange it systematically. And we've arranged that systematically like this. This diagram is called a Hertzsprung-Russell diagram. Let me get out of the way here so you can see it better. It was named after Einar Hertzsprung and Henry Norris Russell, who came up with it at about the same time. And you can see on the bottom, if you take a look on the bottom axis here, there are O stars, B stars, A stars, F, G, K, M stars. And over here on the right-hand side, there is all the way over, there is the star's luminosity, written in terms of the luminosity of the sun. So the 1 here means the same luminosity as the sun. And this 10 means 10 times the sun's luminosity. And this 100, 10 squared, means 100 times the sun's luminosity. 1,000, 10,000, 100,000, 1,000,000 times the sun's luminosity. Whereas down here, we have 1/10 of the sun's luminosity. 1/100th, 1,000, 1/10,000, 1/100,000th. So you can see the range in a star's luminosity, this tremendous range in luminosity here. But really, there is not that big a range in temperatures. And on the very bottom here, you can see the surface temperature of the stars. And the surface of the stars are starting out with around, 3,000 degrees here, you can see. There's 3,000. If I move away, you can see 6,000, 10,000, 30,000 degrees for the surface temperature. And this diagram shows where the stars in the sky fall. Now you might think, stars are way different from each other. They're going to be scattered all around, but they aren't. Stars occupy a strip that runs from the upper left down to the lower right there. And that is called the main sequence of the HR diagram. And 80 to 90% of stars are found there. So what do those stars have in common? What's going on? We will find out that all of these stars are changing hydrogen into helium. They're going undergoing nuclear fusion in their centers, changing hydrogen into helium, and that's where they're getting their power. Now, what happens when stars run out of hydrogen in their central cores and hydrogen fusion is no longer possible? Well, that's where these other stars are going to come from, as we'll find out next week. And we'll find out where these giant stars and these supergiant stars come from. And then we'll find out how low mass stars end up down here as white dwarf stars, as you can see in this oval, that runs along here. So that's a story for next time. But this is astronomers' great organizational diagram. If you go to astronomy talk anywhere, you're going to see an HR diagram of whatever they talk about, because that's how we organize information. So we can learn an awful lot about stars. And more. About half the stars in the sky are binary stars, two stars orbiting each other. So neither star stays still while the other star moves around it. They both orbit their common center of mass. And we can tell where that center of mass is. And just like two people balanced on a teeter-totter at the center of mass, these two stars, in a sense, are balanced on nature's teeter-totter in these binary star systems. And so we can find out the masses of the stars using Newton's form of Kepler's third law. And you'll find out how to do that both in the module introduction and in your textbook. And finally, we can tell how fast stars are moving. Because if you look at the spectral lines of a star, the dark absorption lines that the elements form in the star's atmosphere, well, we can tell also what the atmosphere is made of using that. But you can also, as a star moves away from us, it's racing away from its own light waves. And as it's moving toward us, it's catching up with its own light waves, and that makes a difference. It's sort of like what happens with sound waves. And that's an effect that was first discovered by Christian Doppler a couple hundred years ago. He had a bunch of cars, some railroad cars rolled by him, and there were people standing on them blowing trumpets, and Doppler was listening to a difference in pitch as the car moved by. If you've ever heard a train pass by a crossing and it's blowing its horn, or maybe an ambulance passing by, you know what it sounds like. It's over here, and it passes you by, and it goes, as it's approaching, higher pitch, going away, lower pitch, higher frequency approaching, lower frequency going away. So it sounds like meow, meow. Because moving toward us, this horn, whatever it is catching up with its own sound waves. That forces the sound waves together, so you get more of them per second going by. And as it moves away from you, it's pulling away from its own sound waves. The distance between the waves is longer, and that means you hear fewer of them per second. You hear a lower pitch. Same thing with light. And so if a star source of light is moving toward us, the absorption lines in the star's spectrum shift to blue because the star is moving toward us. It's catching up with its own light waves. That's compressing the light waves, so more meter eye per second. And that is a shorter wavelength of light because the wavelength is being compressed. And that is blue light, shorter wavelengths. Now, if a star is moving away from us, then it's stretching out its light waves. The light waves are becoming longer. And a longer wavelength light is red light. And so we call that a red shift. And the spectral lines shift toward the red end of the spectrum. And so from a star's Doppler shift, we can find out the star's velocities in space. We know an awful lot about stars for not being able to send a probe out to them. And all of these, I mean, astronomers need all the clues they can get to understand the stars. All of these are important. So and there are also other relationships. There's relationships between a star's mass and its luminosity. Once we find out the mass, we can compare that with a star's luminosity and see if they're related. And they are by a mass-luminosity relations. So there's all sorts of things. And you learn all about them. I know I've been talking for a long time, but that's because there is a lot going on. This is one of the most mathematical chapters. But again, don't be afraid. I'm putting math on the homework because I want you to see how astronomers do their work. But on the exam, no, don't worry about it. So, well, I've taken up a lot of your time. The vernal equinox is Monday. I do want to show you what you can see if you go out at night. Real quickly here at the end, I'm going to pull up Stellarium. So let me do that. I'm going to share the screen and pull up Stellarium. There we go. So there's Stellarium. And this is what it's going to look like on the 22nd. So that's going to be Wednesday. And it's going to be only at 10 minutes after 8. So the sky is still going to be, fairly light. But if you look in the west, so if you're up high, you can look out to the setting sun setting over our mountains in the west. You should be able to see a line of bright lights. You'll be able to see Jupiter. And then the moon, which is just a bare crescent moon. And then up here, the planet Venus. And that is going to be pretty cool. And you can see that over the next couple nights, the moon will pass Venus. So it's going to be really pretty because Venus is bright. The crescent moon is getting larger and larger, and it'll just be a pretty sight to see in the sky. So take a look. Well, this you might feel like, oh my gosh, I'm going to be drinking from a fire hose, but no. This will be fine. I'm going to show you some things, but just try to get the idea of all the ways that astronomers have of learning about the stars. I think you'll be really amazed at how very clever astronomers have to be to understand the stars around us. I want to see understand the basic data, like Darwin understood, how shells were interrelated. We understand how stars are interrelated. We can start to work out life histories of the stars. So next week, we're going to talk about stellar evolution, these changes that a single star goes through in its lifetime as it burns through one type of nuclear fuel after another. So until next week, hope you enjoy learning about this. I really do, because I love this stuff. So enjoy. If you have any questions, you can contact me by email. You can be happy to meet with you by Zoom, or you're welcome to drop by my office. So until next time, enjoy spring. Bye-bye.